Hello, hello. I think I'm recording. Hold on. Hello, can you hear? Yeah. So 9.3. Oh, there's three. I forgot to do some stuff in 9.2. I mean, 9.2 was long enough, right? But let's three more things. Get the buttons to work. That would be great. There we go. Right, so 9.2. Three minor. Well, they're not really minor, so I don't want to say that. Three more things, and there we go. Three more things. Okay, so the first one, the first two, I guess, are just general things about series and how they converge or sort of diverge. Let me find it so I don't butcher it when I talk about it. I have to go into my, because I rewrote my notes and I just left it out, so I got to find where I originally had it in my old notes. I don't feel like pausing the video, so I'm looking for it. Oh, found it. Okay. Jeez. Sorry about that. So first off, you can kind of if you have an infinite series and you know the thing is convergent, you can kind of do a lot of the stuff that you did with finite series. Okay, so you can like apply distribution laws and cut up sums and things like that. So the first thing I want to say is that if you have convergence, so I'll just kind of imply that if this thing adds up to something like A, and this other thing adds up to something like B, then we can say that well, two things you can kind of factor out things from the series. So both of these series are infinite types, right? They're not the finite types. And if you ever study like discrete math, is usually I think where you would pick it up. There's like a difference between the finite sums and the well, maybe they introduced that in Calc 1 back when you were doing integration, when you first learned about Riemann sums. So you could it's just like if you had two terms, you could factor something out. If you have 20 terms, you could factor something out. But if you have an infinite number of terms, that might not necessarily happen. So you have to be very careful in those cases. But if you can, if you could say that these things are convergent, then you have some power. So if you can notice there's some constant times every term, you could factor those terms out of the summation, so long as it's convergent. And then likewise, you could split these things up. So if you have a sub n plus or minus b sub n, and you know that each series alone is convergent, then you could split them up and kind of, for whatever purposes. Sometimes it helps to go one way or the other way. But anyways, this will end up equaling, the first one will end up equaling C times A, the second one will end up equaling A plus B. Okay, so that's the first thing. The second thing is really super duper important. This is one of the most important kind of tools you'll have for, and it's a starting place really. Whenever somebody hands you a series, this is the first thing you check. It's called the nth term test for divergence. And it's very simple, okay? It's basically what you do is, for example, you'll be given a series, and we'll say maybe very simply it just has 1 for its nth term formula, okay? So say n equals 1 to infinity. To prove that it's divergent, one thing you could do is just take the limit of that formula, that nth term formula, 1. Okay, so you take the limit of 1, and if that thing is not equal to 0, it's divergent. The series is divergent. So I see the limit is 1, that's not equal to 0, that implies it's divergent. Okay, so that's the way it works. So I'll say part A here. If the limit of the terms of the series, so the series we're talking about is a series A sub n. If the limit of A sub n does not equal 0, then the series, this A sub n thing, is divergent. You can always apply our logic to these things. I guess logic would be incorporated in the, so sort of think of math as a language, and then there's a meta language attached to it where you can talk about the language of math. But kind of the instructions for math, part of it, you have all these rules of algebra, but there's also rules of logic that will allow you to manipulate the language a bit. So in that sense, you could see these statements in a more symbolic form. You could say if blah, then blah, right? So instead of saying blah and blah, you could give those things names. You could say if P, then Q. And then we could abstract it even more with some symbols, where that arrow symbol means if then. Okay, so if P, then Q. If you study logic, there's all these equivalencies, and it's kind of an algebra all of its own. You can sort of say that this is completely equivalent to something called the contrapositive, and the contrapositive it basically says you reverse the implication and negate both sides. So that if P then Q is logically equivalent to not Q then not P. Okay, so there's some fallacies involved there. You can't say if Q then P and say that's going to work, right? That's the whole hit the baseball out of the park kind of argument. So if I get a home run, if I hit the ball out of the park, then I get a home run. But if I get a home run, that doesn't necessarily mean I hit the ball out of the park, right? You can get it inside the park home run, right? So there's these logical fallacies, converse and inverse fallacies. You have to watch out for. The only one that works is this contrapositive. And so with regards to the P and the Q's that we've established here, where the P term is the limit is not equal to 0, and the Q term then is the series is divergent. If we negate each one of those, in other words, take the opposite of the expression. So I'll say if, and now I have to reverse those two. So I'm going to put the series first. So and to negate it, I'll say instead of divergent, convergent. So if the series A sub n is convergent, then this limit will equal 0. Oops, the limit. I'll put that there. Of A sub n is convergent, or is equal to 0. Sorry. Is equal to 0. Okay, so you could say that this direction is not used very much. What's used a lot is one of the fallacies, right? So everybody wants to say, well, if the limit of the terms is equal to 0, then the series must be convergent. But what I'm saying is that that's one of the fallacies. I forget if it's inverse or converse. I think it's the inverse fallacy, but the fallacy that I'm worried about is you saying something like not P, then not Q, right? This is bad. So I'll just write over top of it in red, bad. And everybody wants to do this. Well, not everybody. It's mainly the students who aren't doing their homework and are not really invested. But this does not work. So if the limit of A sub n is actually equal to 0, then you can't really say anything about the series. The series A sub n may converge or diverge. So it's kind of a useless thing to even check upon. Anyways, let me find, was there any of these problems in the homework? Goes to the next question. And I'm looking, and probably, Of course, I didn't list them in my notes. So let me just take some from the actual book then. So number 9, we have the series n all over n plus 1 from n equals 1 to infinity. So to check it, to see, so you can automatically tell it's divergent if that limit of the terms of the series equals 0. Okay? So take the limit, and of course this limit is just 1. That's not equal to 0, so therefore I'm done. It's divergent. Okay? You don't have to worry about, is this a telescoping or is this alternating? And we're going to get all kinds of different series here coming up very quickly. But at this point, you're done. So it's an easy test to do. And yeah, okay. So another one, tan inverse of n for this series. And yeah, so we take the limit. And again, all these limits go to infinity of tan inverse of n. Again, the tan function is just the reflection of the tan function. Tan inverse is a reflection of the tan function about the line y equals x, and then it'll have these asymptotes. So as n goes to infinity, the tan function is going to go to pi. The tan inverse function, excuse me, is going to go to pi over 2. That, of course, is not equal to 0. Therefore, it is divergent. Okie dokie. So that's the second factoid I needed to give you. Extremely important, okay? This is kind of the starting place for any given series. The starting place. We don't have a lot to work with at this point. We only have like 3 factoids that we could really use. You test for telescoping, you do the geometric, look at geometric series issues, and the nth term test. Okay, the next factoid is, and I don't want you to abuse this because technically you may not be allowed to have your hands on this information yet. It's classified. Just kind of like if the even terms go to one place and the odd terms go to another, it's divergent. Kind of the subsequence factoid, which you would get later on in life. That one's kind of classified as well. This fact is kind of classified, so you don't abuse it, but it helps in a pinch. And basically what it says is that if the series a sub n converges, then you can multiply it. And we could say this converge or diverge. So let me make it a little more succinct so I don't have to write 2 implications. If the series a sub n converges or diverges, then the series of a constant times a sub n will have the same behavior, where the constant is non-zero. Okay. So some examples of that, and you could just look above to problem 53. Okay, so I know that the series tan inverse diverges. So what happens if I multiply tan inverse by 1 over 1,000, right? Is that somehow going to nullify the divergence? And no, it's still divergent. Okay, so it diverges because this series tan inverse of n diverges. Okay. And then likewise, if it's convergent, so we can think of an example very quickly that's convergent just by alluding to the geometric series. So we know that this is a convergent geometric series because the r value is less than 1. The absolute value of r is less than 1. What about then? So this converges. So some whataboutism. Well, what about the series? I don't know, a million. Maybe if I multiply it by 1,000,000, somehow it's going to be divergent, and that turns out that's just not true. Okay, so it's still going to have the same behavior. Okay. Along with this idea then is I guess it's not just 3 more things, it's 4 more things. But well, you know, this is not a lot of fun for you, I'm sure, but let me get my composure here. This is just stuff that's going to help make your life easier, okay, honestly. Basically, you can chop terms off of series, and it's not going to affect the behavior. So if the series n equals 1 to infinity of a sub n converges or diverges, then the series n equals some other number m to infinity has the same behavior. So you can kind of keep in your mind this motif of eventualities. If it eventually always behaves a certain way, it's not gonna, it really won't matter what it did in the short term, okay? So for example here, maybe we have something like the series from, and this is one of the reasons why I often don't put that lower index. That's just my thing. So if you have the series from 0 to infinity of -1/2 to the n, you know that's geometric. The absolute value of r is 1/2. It's less than 1, so it's convergent. Okay. If you know that's true, then you can say, well, n equals 1,000,000, or let's just keep 100,000 to infinity of -1/2 to the n will also be convergent. Okay, so convergent, so shortened, I don't know how you want to say it, but shortened series is convergent geometric. So we kind of have to still let the reader know that this is that type of series. The only kind of caveat here is you cannot be all like, well, the sum is going to be 1 over 1 plus 1/2. Then, no, that won't work because you're missing terms. That does affect the sum. Okay, so the actual value of what it would equal if you add it all up is going to be affected at this point. Okie dokie. So that will conclude then 9.2. I apologize if you got into the homework and we're all of a sudden, oh my God, how do I do this? I apologize. Okay, so let me put my notes back together here and we can get into 9.3. Okay, so 9.3, the first part is you're going to see these series. So if you look back at this one series, this guy right here, you may or may not remember that integral from the last test, the integral of tan inverse of x dx. And of course, to do this, you have to do by parts. You have to say, all right, u is equal to tan inverse, because you know the derivative, right? The derivative tan inverse 1 over 1 plus x squared. dv, then that's the troublemaker. You're like, well, what the heck should dv? There's nothing there. Well, it's just 1 dx. And then you could do your v and your du and then do by parts, right? So I would hope that it's somewhat in your brain that, look, if I just replace that summation symbol with an integral symbol, I could actually do some work, and doing work is fun, right? Well, yeah, and not only is it fun to do, and I'm being sarcastic, it's not fun, but not only is it fun to do something like that, it's useful, believe it or not. So you can make conclusions on series by doing the integral, the improper integral of the terms of the series, okay? And it's called the integral test. So we're going to get the integral test. Basically, you just take the integral of whatever sitting in. There's restrictions. You can't do it all. You can't be crazy with it. So you have the integral test, and then you also have these p series, which will always be confused with your geometric series from this point on. But anyways, basically, we'll start with the integral test. And for the integral test to work, you need three things. You need, so you're going to be given a series a sub n from n equals something to infinity. Just say 1 to infinity. And you consider a function that kind of mirrors that a sub n, right? So you're going to say f of x is kind of like this. You're just going to replace that formula a sub n with some x's. So I hate to write it that way because it looks like I'm doing statistics all of a sudden. I'm not. But there it is. Okay, so given this series, you consider this function that you kind of generate, which mirrors the terms of the series. And then you're going to compare the series and the integral. So compare the integral of f of x dx from 1 to infinity and the series from 1 to infinity of a sub n. And there's some caveats here, right? So you have to make sure several things. And my pen stopped working again because I accidentally hit the button. F of x needs to be positive, so continuous and decreasing eventually. So it's one of those things that has to always be doing something so long as you get out far enough. So in the beginning, it could go up and down, but if it eventually conforms to these three characteristics, then you're good. But anyways, f of x needs to be positive, continuous, and decreasing eventually. Okay. If that's all true, then both of these characters will have the same behavior. So both, I don't know what to call them, things will behave the same. Okay. The sketch of the proof. So why does this work? It goes to inscribed and circumscribed rectangles. So this is an idea you should have seen in Calc 1 when you're building Riemann sums. You can use left endpoints or right endpoints, and sometimes if the curve is behaving in a certain way, all the rectangles will be below or all the rectangles will be above the curve. Okay, and you can reinterpret the summation as a sum of a bunch of rectangles, so long as the width of the base of the rectangles is 1, right? So I'll say starting at n equals 1, and of course now the stupid pen isn't working. Okay, so I start at n equals 1, and then 2, 3, and this curve is our f of x, but it's also, a sub n if you just had a bunch of dots there without the continuity. But anyways, 1, 2, 3, and this time we're gonna inscribe the rectangles. So put the rectangles with the right endpoint for the tops of the rectangles. Okay. And then we keep going on, and then we'll get up to these last two, so n minus 1 and then n. And again, we have the right endpoint. I have to smush that in so it's below the curve there. Right, so the area of each one of these, if you think about it, the area of that particular dude is just going to be f of 2 times the width of the base. But the width of the base is just 1, so it's just going to be f of 2, which is equivalent to a sub 2. So the summation, what it's going to do is basically just add all of these up. It'll be a sub 2 plus a sub 3, and there's your series, right? All the way up to a sub n. Let's put that in summation notation. Unfortunately, it doesn't start at 1, but that's okay because all that junk I was saying about that You can basically just kind of forget about the first couple terms. It's not going to make a big deal. Okay. So anyways, you'll have n equals 2 to n of a sub, we have to call it something else, a sub k. And then what we're going to do is compare that to the integral going from 1 to n. Okay, so we have the same function, poorly drawn by me, from 1 to n. And this time we can do the integral of it and get the actual value. And because the rectangles in that first picture are all below the curve, and because the curve is decreasing and positive and all that junk, we could definitely get this inequality going on. So this will be f of x dx from 1 to n. And then this will be less than or equal to, now what we do is circumscribe the rectangles. So put the rectangles over top of the curve. So again, 1, 2, 3, blah, 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 all the way to n minus 1 times n. And of course, this time, the rectangles will have the right as the endpoints. And so the summation of those terms there will be bigger than the integral because those boxes. So what you have there is a sub 1 plus a sub 2 plus dot 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 plus a sub n minus 1, and of course that will just equal the sum from n equals 1 to n minus 1 of this a sub k. Let me fix the indices here. So let's make this k to n. I apologize on both these. And it's not just my fault, it's a stupid book. The book insists on kind of avoiding these issues with the indices, and they cheat their way around it, okay? Sorry, I had to be said. I shouldn't be, I mean, if it wasn't for the book, I wouldn't have a job probably, but all right. The book has taught me a lot. I owe a lot to the book. I've learned almost everything I know from well, the books. Let me say the books. I don't want to just give them props, but all right. So anyways, what are we dealing with here? You have an nth term sum formula, which is, you know, back when we first started, you could basically say something about an infinite series if you look at the limit of the nth term, right? So s sub 1 would have been a1, s sub 2 is a1 plus a2, blah, blah, blah. S sub k is a1 plus dot, 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 all the way up to plus a sub k. And then to figure out what the actual sum of the series is, you just take the limit of s sub k. So what you're getting on the right and left of this inequality are these kind of expressions. You're getting basically s sub n minus a sub 1 on that side. And then on the other side, you're getting s sub n, what is it? It's missing the top term, minus a sub n. And it turns out that those things won't really affect you. S sub n minus a sub n is basically just s sub n minus 1, right? And the limit of kind of the you know, it's a comparison of saying, all right, I have the sequence a sub n equals 1 all over 2 to the n, right? So what's going to happen to the limit of a sub n equals 1 over 2 to the n minus 1? They'll both go to the same place, Buster. You could prove that using the strict definition of the limit, but let's not say we did, right? So anyways, okay, so the proof of it is that you could take the limit of all three sides now, and basically taking the limit of the middle part is equivalent to just doing the improper integral. So you'll have the integral from 1 to infinity of f of x dx, and then if this thing diverges, so if the series diverges, what's it going to do to anything that's above it? Well, it's going to push that thing into the land of divergence, right? So you could like say the integral from 1 to 1,000 is big. And then the summation above it, the finite sum above it, is going to be real big too. And then you could say 1 to a billion is going to be even bigger. The thing above it is going to be even bigger than that. And you can play that game. No matter how big you make this integral, that summation is going to be bigger than that. And that's kind of it. You know, that it's going to go to infinity as well. So that if the integral diverges, it's going to force the limit of this s sub n minus 1, which is really just the series with a different index on the top. It forces this series to diverge as well. And then likewise on the other end of things, so this is kind of the first factoid, on the other end of things, if the series from 1 to infinity, if the improper integral converges, it's a little more delicate here. In this case, it will, it's going to bound the S sub n sequence of partial sums above. As it bounds basically S sub n above, thus from the initial conditions where a sub n is always positive, so these terms here, if f of x is positive, continuous, and decreasing, this thing is also going to have the same characteristics because that's what you based f of x off of. So a sub n is positive, well, it's not continuous, but it's positive and decreasing. And so whenever you make s sub n, whenever you add another term to s sub n, right, because that's how you're creating these sequences of partial sums. S sub 1 is a sub 1, s sub 2 is a sub 1 plus a sub 2, etc. You're going to get an increasing sequence or a non-decreasing sequence, and it's bounded above, and so by the monotonic convergence theorem, it's going to be convergent. Okay, so let me read what I have. If the integral converges, it bounds S sub n above, thus S sub n is increasing and bounded above. And thus convergent by that 9.1 theorem, the end theorem in 9.1. I just call that by the monotonic convergence theorem. Okay, so that's the big and small of it. Basically, you can kind of reinterpret these summations as sums of area of rectangles, and then you can put the areas below or above this integral. And if the integral diverges, you can kind of imagine the rectangles being above that infinite area. So it too must be infinite. So, I mean, I'm building kind of a lot of intuition. Ultimately, you need to get your hands dirty, though, and really get in there and, go back to all the definitions and make your entire system, your formal system, a bit more strict, a bit more formal, I guess is probably what we should say. But anyways, long story short, it's not that big of a deal. The hardest part is just showing that these functions are positive, continuous, and decreasing, because you're probably not used to doing that. So let me get into the bulk of what's going on here with homework. So I'll just call these examples. And you would do all this stuff in, like, they would call it like an advanced calc class. You would get more involved with the theories and the theorems. Okay, so I would hope, hopefully I'm not misleading you. I mean, honestly, I learned most of the stuff when I took Calc 2, but I'm from a different generation, so that may not be the case with the younger people. But anyways, here is a series. So what's going to happen is you're going to be given a series, like I was bumbling on about in the beginning of the lecture, such that you may recognize it as something that you could integrate. Okay. Okay, so here I am, I'm looking at this thing and I'm saying to myself, hey, that thing looks like it would be pretty easy to integrate, right? So I need to make sure then that it fulfills the criteria. So first, and we consider the criteria only on the sort of the domain of the summation. So it's going from 1 to infinity. Okay, I don't care what it does at negative 1,000. So long as it's continuous, positive, and decreasing on that interval, I'm good. Okay, so is it continuous? Well, yeah. The only discontinuity is where the denominator is equal to 0. That's just how rational functions behave. So yes, the denominator is only 0 in the negative numbers, so we're good. Is it positive? Well, the numerator is positive. The denominator is, on this interval at least, positive. A positive times a positive is positive. So yes, on this interval, it will be positive. So I just make some sort of mini argument there. It's not a very good argument, in my opinion. I've been spoiled, but there it is. It's something. Then thirdly, and this is the part I'll be most interested in on the test, can you take a derivative? Because we want to show it's decreasing. Right? So is it decreasing? How do I show it's decreasing? You take the derivative and show it's negative on that interval. So, I mean, usually what you'd have to do is take the derivative, find the critical numbers, do a number line, all that jazz. All right. But on the test, what I want to see is a derivative, because I need to make sure that all of you guys know how to take derivatives, which you should know how to do by the time you get the Calc 3 or any engineering class. Right. So can you take a derivative? Well, let's see. I do a power rule. So I'm going to bring down the -1 from the exponent, -2 times 3x plus 9, subtract the old exponent by 1, and then multiply by the derivative of the guts, which is 3. And then look at it. So I got -6 all over 3x plus 9 squared. Okay. How does that compare to the number 0? Well, the numerator is negative. The denominator, because it's something squared, will always be positive. A negative divided by a positive is negative, therefore this is less than 0. And that on that interval, the whole number line except where the discontinuity is, it will be negative. But this implies what? It implies it is decreasing. Okay, so I need to see on your test the derivative, and then saying the derivative is, then I need to see that inequality. Okay, you just need to put, you could even almost just lie to me and put an inequality there that says it's less than 0. I may not even notice. I probably will, but okay. So once all that jazz is done, then, and I'm going to warn you in the homework, it's not asking you to do that, but you should, because on the test you're going to have to do that for step 3. Now, finally, I can do my integral. Honestly, you can start the integral wherever you want. So if you need to push that number 1 out to 10 to make your integral work, it's fine, because that will be kind of equivalent. You'll have a chain of logic due to the 3 more things, right? The pushing it out, you'll be able to prove that this thing is convergent or divergent, and that will imply that this thing is also convergent or divergent. Okay. All right. So, anyways, you can integrate this character. It's 2 all over 3x plus 9. I know what I just said above was kind of scary because I went in the other direction of the implication, but I think it'll work. Sometimes I just guess and deal with the consequences later. It's probably not a good thing if you're building bridges, but I'm not building bridges, so. I'm building people who need to build bridges. I'll be more careful in the future. All right. So the limit as b goes to infinity, I'm going to replace that upper limit with a b. I have then 2 all over 3x plus 9 dx. And then I'm going to say the denominator is a good u sub candidate. So get du is 3 dx. Your dx is du over 3. And then I do my limit. I'm going to drop all the bells and whistles here for a second. 2 all over u times du all over 3. So that's a natural log with a 2/3 constant out front. Absolute value, don't forget, back subbing, it's 3x plus 9. And then put all the bells and whistles back in. Just a warning, in engineering, they usually don't put that limit symbol in there. They'll just put the infinity sign on the bracket. Usually I can tell a student is kind of getting their information off the web when they pull that stuff. And I don't know, maybe some people have already taken Calc 2 and somebody trained, an engineer was the teacher, but it's not likely. So anyways, 2/3, then you have the ln of the absolute value, 3b plus 9 minus 2/3 ln of 12. And of course, then the ln as b goes to infinity, the natural log is going to go to infinity. So this will be an infinity minus L form, which will be infinity, which is divergent. So hence the original series diverges by the integral test. Fun? No. But it is kind of a direct way to get information about these series. And okay, let's try number 2. So here we have 1 all over 8 to the n from n equals 1 to infinity. This dude is clearly geometric. It's kind of shifted over by one place. So I know it's convergent, right? The R value is 1/8. But we need to use this new method. So I'm going to, have the answer. Okay, great. So I have 1/8 to the x. For calculus purposes, I'm going to rewrite that as x to the -8. And then I'm going to go through the questionnaire, right? So I need to concern myself with the interval from 1 to infinity. So is that continuous? And I guess exponential functions are continuous everywhere. Secondly, is it positive? Yes, again. You can never get that thing to equal a negative number or 0. Thirdly, is it decreasing? Okay, so this is the troublemaker, and it's why I wanted to do this problem, just because people forget how to take the derivatives of this kind of thing. So for the derivative, you automatically get back the original expression with now log of 8. Okay. Then you do have to do a chain rule. Okay, so this is the first part of the derivative, and then times the derivative of the exponent, which is, in this case, -1. Okay. Basically, if you don't remember how to do that, you can get your hands on the formula by just converting this 8 to the -x into e to the ln of 8 to the -x, which is e to the -x ln 8, and then take the derivative of that with the chain rule. So it'd be y prime equals e to the -x ln 8 times -ln 8, which is then converting back 8 to the -x. Put that negative up front so it don't look crazy. And there it is. Okay, so there's our formula. The factors of that formula are positive, right? So this thing is always positive. There's no number you can put in for x that's going to generate a negative or even 0. And then ln of 8 is also positive. So what do you have here? You have a negative times a positive times a positive, and then we're comparing that to 0. and that is truly going to be negative, so therefore it is decreasing. Okay, so I can do the integral test. So let me rewrite it again in this other form. Okay, so the next kind of issue is how the heck do I integrate that thing? So let me again drop the upper limit, let b go to infinity, 8 to the negative x dx. So it's kind of just the reverse of the derivative. So instead of multiplying by an ln 8, you're going to divide by the ln 8. So you get the limit of 8 to the negative x. There would be a u sub for the negative x, and that would result in a negative. And that will be all over ln of 8. And then you're going to let x, or rather b, go to infinity here. Okay. Again, the kind of way you would do it would be, if you didn't have any clue, would be to translate it into an exponential and then do a u sub for the exponent. Okay, so then you would take this, and that would be your u sub, and your du would be negative ln 8 dx, and so you'd have to be dividing by negative ln of 8, and that's why you get what you got. All right, so yay! All right, moving along. Then I'm going to evaluate this critter at b and 1. So I get, and I'm going to rewrite it a little bit, so don't be shocked. 8 to the b ln of 8, so I just changed the negative exponent, bring it down to the denominator, and then inputted the b value, minus, so it become plus, 1 all over 8 ln 8. Okay, so that makes it a little more easy to evaluate. The first term is going to go to 0 because it's an L over infinity form. So this will just shoot off to 0. And that will equal 1 all over 8 ln 8. In other words, it's convergent. Hence, this series, the series 1 over 8 to the x, or n, is also convergent, which is what we knew already. Okay, so one point of interest here, note the actual sum is not going to equal 1 over 8 ln 8. And every year on a test, somebody wants to try to convince me that it does. Like I'm going to get on the spaceship and leave the planet and go live with aliens. No, I'm sorry. I don't believe you. And I don't think that's going to pan out. But it's a geometric. It's just not in the form. So I'd have to go n minus 1 is 0 to infinity, 1 all over 8 to the n. Then you could do some sort of substitution. So let j equal n minus 1. So n would equal j plus 1. So I have the sum from j equals 0 to infinity of 1/8 to the j plus 1. Let's just write this as j times 1/8 to the 1. So the a value is 1/8, and then the r value is 1/8. So it's definitely convergent. So it'd be 1/8 all over 1 minus 1/8, which would be 1/8 times 8/7. In other words, 1/7. So lo and behold, some evidence that these things are not the same, right? They both will have the same behavior. Yeah, you can say that. But you cannot convince me that just because one equals 1 over 8 ln 8, the other guy is going to equal 1 over 8 ln 8. So don't try it on my test. Okay, let's move on to number 5. So we have the series n equals 1 to infinity of the ln of n all over n to the 4th. Okay, this one you may think to yourself, well, hey, I don't know if I can integrate that, but you're going to have no choice sometimes. It's not telescoping, it's not geometric. The nth term test won't work on it because it's going to equal 0, right? The limit as, n goes to infinity. I mean, you can do L'Hopital's here because it's infinity over infinity. So you get 1 over n to the 5th. That will equal 0. But that's the bad case, right? Just because the limit equals 0 doesn't imply that the series is convergent. So that is of new use to us. All right. So is it continuous? Well, the ln of x is continuous everywhere. And so the denominator is not, but it's only not continuous in an area where we don't care, right? We only care about the 1 to infinity or further out. You can, if you don't like 1, you're afraid it's 0, maybe positive isn't the same. Is positive, does positive account for 0? You know, do I have to say non-negative to include 0? So if you're not sure, you could push it out to 2 to infinity, and it's darn sure going to be continuous and positive on that interval. Okie dokie. So the question I leave for you then is decreasing, and I think this is the hard one. We have to do a derivative of that thing, and that's not going to be pretty. Okay. So low d high, got to do quotient rule, low times the derivative of the high minus the high times the derivative of the low, all over the low, squared. Okay. Then I'm going to simplify the junk out of that. So that would be x cubed minus 4x cubed ln x all over x to the 8th. I can factor out an x cubed. Maybe that'll make life easier, maybe not. 1 minus 4 ln x all over x to the 8th. I hate to do that because it seems like I'm introducing problems, but so long as x is not 0, it's probably going to be okay. 1 minus 4 ln x all over x to the 5th. And so what? Right, so now on the interval, so on 1 to infinity, or 2 to infinity if you'd rather, x to the 5th is definitely greater than 0, right? Anything I put in there, x to the 5th, if you take, 5 to the 5th power is going to be greater than 0. Anything in that interval is greater than 0. Okay, great. So the troublemaker is going to be this 1 minus 4 ln x business. And I want to see where that thing's equal to 0. So it's kind of like you're finding the critical number, right? So it's 1 equals 4 times ln x. Ln x equals 1 over 4. Exponentiate both sides. So x is e to the 1/4. Okay, e to the 1/4, if you don't know off the top of your head, is like 1.28. Right? And I don't know that. I just have it in my notes. Right. So anyways, you could kind of now do your analysis. So here's my number line. Let's push it back to 1, even though I only care about what's happening after 2. 1.28 is in here somewhere. Okay. Let me get rid of that pesky 2 because I don't really need it. I don't want to nasty up my number line with all kinds of baloney. All right, so here's 1.28. I'm going to do a test value, sign, and conclusion. So my test value I'll put in as 1.1, I guess. And plugging that into my derivative up here, and really all I need to do is look at the numerator. I'll have 1 minus 4 ln of 1.1. I probably have to put that in my calculator. I think it's going to be positive, though. I should have picked my numbers better. I apologize. 1 minus 4 ln of 1.1 is positive. So it's positive or positive. So in that interval, it's positive, and therefore it is going to be increasing, which is bad. But once you get past 1.28, so let's take a test value let's pick something that actually is going to be somewhat useful, e to the 5th, right? So I can plug that in. 1 minus 4 ln of e to the 5th is 1 minus 4 times 5, which is definitely less than 0. So this will be negative, and it's going down. So anyways, on the interval I care about from 2 to infinity, so I have to push it out to 2, unfortunately. This will be less than 0. Okay. So you're going to see that in my integral as well. I'm more old school. I think in the homework they would probably allow you to get away with just going from 1 to infinity, but I'm going to push it out to 2 to infinity, and then just argue that adding one more term isn't going to make it all of a sudden miraculously diverge or converge. So I'll have then ln x all over x to the fourth. So more fun, right? How the heck do I integrate that thing? It looks like by parts. I hate to be the bearer of bad news, but yeah, by parts. So I'm going to let to equal, the thing I know how to take the derivative of is ln x, and then dv is this x to the negative 4. You can't just put x to the fourth in there. That ain't going to work. Du is going to be 1 over x dx. And then v is going to be negative 4x to the negative 5. And then we could do our baloney. So I'm going to drop the limit part of it in front, and then I'll have negative 4x to the negative 5th ln x. Remind yourself to evaluate eventually, plus, so minus negative, 4 integral 1 over x, that will be to the 6. dx, so x to the negative 6. And then this will be the limit of negative 4x to the negative 5 ln x plus 4. So x to the negative 6 plus 1 is x to the negative 5th, then divided by negative 5. All kinds of helper parentheses there. Then I'm going to do a limit. So I need to evaluate all this crud. I'm going to rewrite it a bit. 4 ln x all over x to the 5th minus 4 all over 5x to the 5th. And then I'm evaluating from 2 to b. Okay. So now I'm going to start plugging in my b, and we're doing a b going to infinity. So it's negative 4b ln b all over b to the 5th minus 4 all over 5b to the 5th minus negative 4 ln 2 all over 2 to the 5th minus 4 all over 5 times 2 to the 5th. And of course I run out of room. All right, this dude, we're going to have to do L'Hopital's on it, right? So it's going to be a negative 4 all over, negative 4 times 1 over b times 5b to the 4th. Should be negative 4 all over 5b to the 5th. And of course, that's going to go to 0 as b goes to infinity. This dude will also go to 0. It's L over infinity. And you're just stuck with some constant material. So 4 ln 2, and it doesn't even matter. I mean, on a test, I want to see that you know how to take an integral before I let you out of this class. But there it is, and so it's convergent. And so by the integral test, the series ln of n all over n to the 4th is also convergent. Yay. All right, so please write, as long as I can tell it says convergent. I don't really care very much, but there it is. Okay. P-series. So then ultimately we care about these things that look like this. And please don't confuse this. This is a P-series. This is a geometric series. Okay, the big difference, so if I were to write out the P-series, it would be 1 all over 1 plus 1 all over 2 to the P plus 1 all over 3 to the P plus 1 all over 4 to the P plus dot, dot, dot. Let me give you a concrete example on this other one. Let's just say 1/2 to the n, right? And this is why it gets confusing. when you compare the geometric. The variable on the geometric is the exponent. So you'll have 1/2 to the 1 plus, or 1/2 to the 0, depending on where you start, plus 1/2 to the 1 plus 1/2 to the 2 plus blah, blah, blah. So you see the difference. On the left, the denominator is variable. On the right, the exponent is variable. So for P series, the exponent is stuck. Maybe they should call them exponent series or something a bit more, to the point. But yeah, please try not to get them confused. Anyways, why do they introduce them here and not somewhere else? It's because we can prove the p-values for which these series converge or diverge using the integral test. So consider then the series 1 over n to the p from n equals 1 to infinity. Use the integral test on this. So we have then the f of x formula will be 1 all over x to the p, which is x to the negative p. Is it continuous on the interval from 1 to infinity? And yeah, yes. Is it positive? Yeah. And 3, is it decreasing? Well, barring any negative p-value that would cause it to be like 1 over x cubed, or sorry, 1 over x to the negative 3, which would be x to the third. Barring any of that business, then yes, because you're going to get a negative from doing the power rule, right? So f prime is going to be negative p x to the negative p minus 1. So you'll have that negative in front, and that will be less than 0. So yeah. Okay, so we can do the integral test on this. I'm going to rewrite it as x to the negative p dx. And then there's kind of two cases, right? I could always do power rule except when p is equal to what? Well, when p is equal to 1. Because when p is equal to 1, it's x to the negative 1, which is 1 over x dx. Okay? And when that happens, you're going to get a natural log. And let's just cut to the chase, right? So it's going to be the absolute value of b minus the ln of 1, which of course is 0. But when you take the limit as b goes to infinity, that will equal infinity. So in that case, it's divergent. Okay. This is a very special case. When p is 1, it's also called the harmonic series, which you should kind of have hard-coded into your brain. Okay, the harmonic series is divergent. This series 1 over x, or 1 over n, from n to infinity is convergent. And the one thing about this series is it's extremely slow moving. It's like it would take, if you added one term of that series every second, it would take from here to the end of the universe to reach 1 million. But it still diverges. It's just crazy like that. And I'm probably exaggerating, but I'm probably not by much. Okay, so anyways, that is the case when p is 1. P not 1, so in those cases, you can use power rule. So you get x to the 1 minus p all over 1 minus p. And that will be the limit as of b to the 1 minus p all over 1 minus p minus 1 to the 1 minus p. So that's just always 1 all over 1 minus p. And then it's dependent on the p-value. Okay, so the only part that is affected by the limit is this portion right here. Okay? And that will either converge or diverge based off of what the p-value is. So the other part is just going to go the 1 over 1 minus p, that negative, right? So it's this first part we need to investigate a little bit more. And in particular, we have to say two cases. The first case, 1 minus p, what happens when that's less than 0? And that will be the good case, right? Because as soon as 1 minus p is less than 0, you could rewrite it with the b in the denominator. So that'll drop the b down to the denominator, and you'll end up with a 1 over infinity type scenario. Okay. So that will go to 0, and therefore the overall limit will be negative 1 over 1 minus p, and therefore it'll be convergent. Okay. The other case, when 1 minus p is greater than 0, that's when it's going to shoot off to infinity, right? So that case it'll be divergent. Okay. So overall, the p-series sum n equals 1 to infinity of 1 all over n to the p converges when the 1 minus p is less than 0. Adding p to both sides, that would be when 1 is less than p. In other words, when p is greater than 1. And then it diverges in the other case. So that's when 1 is greater than p. In other words, when p is less than 1. But you also have the natural log one from above where you couldn't use the power rule. So that's going to say it diverges when p is less than or equal to 1. Okay, so this is awesome because now we can just look at a series like like what we did with the geometric series and automatically know whether it's convergent or divergent. So, for example, the series n equals 1 to infinity of 1 all over n to the 7th. So what the heck is that thing? Well, it's clearly a p-series. The p-value is 7, so therefore it's convergent, right? Then they start getting, you know, we can use what we sort of our top secret, our what is that, from above, the 3 more things thing. You can multiply it by a constant. It's just a multiple of a p-series. P equals 7. So therefore it's convergent. And on tests, you're going to have to do this. You're going to have to say, you know, what type of series is it? What's its defining criteria? Is it convergent or divergent? You can't just bring a coin into the test and then like flip the coin and write convergent or divergent and be right 50% of the time. That ain't going to work. Okay. All right. They're going to try to trick you, of course. Like 1 all over the square root of n. From n equals 5 to infinity. So the starting place doesn't really matter. Again, that was from the 3 more things. That was our our top secret information that the book doesn't clue you in on. It's just, this is what is the p-value, right? So remember the square root, you can rewrite that as a fraction exponent. It's 1 over n to the 1/2. So it's a p-series. The p-value is 1/2, so therefore it's divergent. Okay, great. I don't know. It's there. It is. Okay, awesome. Thank you for watching, and I'll see you next time. Oh, I forgot to give us a quiz, didn't I? Ah ha ha. So the video quiz. Determine if this series. This is video quiz number for 9.1. Let's try to make it clever like the last one we did. Is this series convergent or divergent? And let's put it as n times the square root of n from n equals 1 to infinity. So you got to write, I'm going to give you a hint. It's a p-series, but then you got to tell me what the p-value is. And then you got to tell me, is it convergent or divergent? Right in this, put that in this box here. Is it convergent or divergent? Okay, so there's a video quiz. Thank you for watching. I'll see you next time.